Slab. Experiment No. 9. Amplitude shift keying, BASK. Modulation. Objectives. To understand the basics of amplitude shift keying, BASK, modulation. To understand the working of amplitude shift keying, BASK, modulation. To implement the Modulator SING 1496. Equipment required. DMM breadboard oscilloscope function generator, dual channel, DC power supply plus 12V, fixed, dash 12V, fixed, resistors 100 omega quantity equals 2. 200 omega quantity equals 1, 1K omega quantity equals 5, 2K omega quantity equals 1, 2.7K omega quantity equals 1, 2.7K omega quantity equals 1, 3.9K omega quantity equals 2, 5.6K omega quantity equals 1, 6.8K omega quantity equals 1, 10K omega quantity equals 5, potentiometers 100K omega quantity equals 2, capacitors 10 NF quantity equals 3, 0.1 UF quantity equals 3, ICMC 1496, balanced modulator, quantity equals 1, op-amp, LM741, quantity equals 1, connecting wires. Theory. In digital modulation, the input signal is in the form of digital digits. It is in the voltage levels either high or low. Amplitude shift keying, BASK, is a type of digital modulation in which the amplitude of the carrier is varied with respect to the digital message. Figure 9.1 shows the basic block diagram of a BASK modulator, in which the balanced modulator provides amplitude demodulation, whereas band pass filter will remove the high frequency contents to make the signal waveform perfect. Figure 9.1 The basic block diagram of a BASK modulator. In a BASK it requires two input signals. First impetus digital input signal and second impetus the carrier signal. Always remember that the amplitude of carrier signal should be greater than the amplitude of digital input signal. If the amplitude of carrier signal is less than the amplitude of digital input signal, then such a modulation lead to overmodulation and undermodulation effects. BASK modulation signal can be expressed as equals plus 9.1, where 0 less than or equal to t less than or equal to ti equals 1, 2, 3, m. In equation 9.1 the values of amplitude I have type piece of possible magnitudes the and denote the cutoff frequency and phase respectively. If wecus m equals 2 the signal will transmit the binary signal. If the binary input signal value is 1, then the carrier signal having fixed amplitude and frequency will be transmitted out. When the binary input signal is 0, the no signal is transmitted. That is why this process is also known as an off-keying, okay, as shown in figure 9.2. Note that this type of BASK can represent only bit/symbol. Figure 9.2 Binary amplitude shift keying, BASK. Figure 9.3 shows an example of 4 BASK signal that can be used to represent 4 different digital symbols. Figure 9.3:4 BASK we have used MC1496 to implement the balanced modulator in this experiment. Figure 9.4 represents the internal circuit diagram of MC1496 where D1, R1, R2, R3, Q7 and Q8 constitute the current source. It provides bias current Q5 and Q6. The Q5 and Q6 constitute a differential amplifier that drives another differential amplifier comprised of Q1, Q2, Q3 and Q4. Figure 9.4 Internal circuit diagram of MC1496 The digital data signal is inputted between pin 1 and pin 4. The carrier signal is inputted between pin 8 and pin 10. The GAN balanced modulator is inputted between pin 2 and pin 3. The TIS control-led B resistor between pin 2 and pin 3. The range of BASK current of the amplifier is determined by the resistor connected at the pin 5. Figure 9.5 Circuit diagram of BASK modulator SING 1496. Figure 9.5 shows the circuit diagram of BASK modulation in which MC1496 comprise a balanced modulator. The carrier signal and data signal are single indeed input. The carrier signal is inputted at pin 10 whereas data signal is inputted at pin 1. R14 determines the GAN and R15 provide us the BASK current to the circuit. If we adjust VR1 or the data signal Amplitude it can prevent the BASK modulation signal from distortion. That just meant off VR2. Will avoid the asymmetric behavior of T signal waveform. Pin 12 off T balanced modulator. Will send the output signal to op-amp, UA741. The C4 R18 R19 and R20 constitute a band pass filter to remove the high frequency content so that the BASK signal waveform will become accurate. Procedure. A. Construct the circuit of figure 9.5 on the breadboard. B. Apply a digital input signal, i.e. highest 5V lowest 0V, 100 Hz wave frequency. With carrier, sine wave, signal of 10 Vpp/10 Khz to the circuit of figure 9.5. C. Adjust potentiometer VR1 until an accurate and distortions-free BASK modulated waveform can be seen in the oscilloscope. D. Then adjust potentiometer VR2 to avoid the asymmetry of T signal. E. Using oscilloscope observe and record the digital input and BASK modulate output. Signal in figure 9.6. Figure 9.6. F. Apply a digital input signal, i.e. highest 5V lowest 0V, 100 Hz wave frequency with carrier, sine wave, signal of 14 Vpp/10 kHz to the circuit of figure 9.5. G. Adjust potentiometer VR1 until an accurate and distortions-free BASK modulated waveform can be seen in the oscilloscope. Then adjust potentiometer VR2 to avoid the asymmetry of T signal. H. Using oscilloscope observe and record the digital input and BASK modulate output signal in figure 9.7. Figure 9.7. I. Apply a digital input signal, i.e. highest 5V lowest 0V, 100 Hz wave frequency with carrier, sine wave, signal of 14 Vpp/20 Khz to the circuit of figure 9.5. J. Adjust potentiometer VR1 until an accurate and distortions-free BASK modulated waveform can be seen in the oscilloscope. Then adjust potentiometer VR2 to avoid the asymmetry of T signal. K. Using oscilloscope observe and record the digital input and BASK modulate output. Signal in figure 9.8. Figure 9.8.